One more applause for Simeon.
Thank you. So, hello everyone. My name is Simeon Kotashki. I'm integration lead for Neon EVM. A couple of words about me. I've been software engineer for 10 years. The last 6 years I've been blockchain engineer, Solidity developer, and currently I'm leading integration with Neon EVM. So, just a quick question. How many of you, I know it's Belgrade, but today we're going to talk about Solana. So how many of you, Solana and EVM, not only Solana, but how many of you have actually interacted with Solana? Okay, that's good. We have some Solana degens here trading meme coins. And and yeah, basically what Neon EVM is. Neon EVM is actually smart contract on Solana. It's not a layer 2. I would say it's more like of a layer 1.5, and it provides like a compatibility extension for Solana ecosystem. What does that mean? It means that from one side, it combines the benefits of the EVM, so you don't need to change your code. You can deploy any EVM dApp on Neon EVM, and at the same time, you can leverage low gas fee, local markets, parallel execution, and access to growing Solana ecosystem. I will go back to some of them, but I can give some example. For example, low gas fees and local gas fees, which is very important. So in Ethereum, how gas market works. For example, currently in Belgrade, you try to order an Uber, but in Bulgaria or in some other country, there's a concert and everyone's ordering Uber. So the Uber will cost you in Belgrade 5 times more because in some other country, it's congested, right? So the gas market in Ethereum is global for the whole network. How it works in Solana is a little bit different. The gas market is local. So if, for example, you have one dApp that is congested, the gas fee will go only up for this dApp, not for the whole network. So you can leverage this. And this is because of the parallel execution of transaction. And we'll see how Solana handles this. Because we use Solana as execution and settlement layer. We are like an application layer EVM. So our smart contract can understand EVM bytecode, execute it, and persist the state in the form of some metadata inside Solana. So what we are trying to achieve is 2,000 transactions per second. Currently, we have achieved 700, but we are doing some tweaks and upgrades, and currently a very, very big upgrade is coming. We just deployed it on DevNet, and we're testing it. So we'll reach around more than 1,000 transactions per second. Gas fees, here it may not be very relevant in dollars because Solana went up a lot, so it may be 5 times bigger, but it's still a lot lower. And on the upper side, you can see what we have, like the EVM, which is actually the smart contract, the proxy server, which is actually our RPC. We're going to see in a moment what it does. Tracer API that you can use for historical data. Our Neon Pass that is basically a bridge. Why I say a bridge? It's because it's actually not a bridge. It's SDK and a tool to transfer natively your assets from Solana to Neon EVM. And because Neon EVM lives inside Solana, you can do it even without this bridge if you want. You just need to be able to compute your instructions. And because most of the users and builders are EVM, come from EVM background, we make the tooling for them to use Neon EVM seamlessly and not be able to worry on how Solana works, because Solana is very different. Some of our ecosystem, as you can see, we support all the dev frameworks, Truffle, which is deprecated, Brownie, Hardhat, Foundry, We support Web3.js, all Open Zeppelin contracts, Remix IDs, MetaMask, and so on. Also, we support Chainlink price feeds, but we read them from Solana natively. I will explain to you in a minute how. And yeah, this is another representation of the dev tooling. And this is a very important diagram. It shows in a nutshell our architecture. So you can see on the right-hand side, we have the EVM program, which actually is all transactions always hit first our program, and it knows how to execute this EVM bytecode inside the Solana virtual machine. And this, we also have some composability features. Currently, they're limited. So, for example, you can see SPL token. So what you can do, this is very interesting. You can use an SPL token. For people who don't know what SPL token is, SPL token is the equivalent of ERC20, but on Solana. And it's a very different standard. There you have one registry, one program that basically commands all tokens, right? You don't have, like in Ethereum, you have one contract, one ERC20, another contract, another ERC20. So in Neon EVM, you'll be able to have a SPL token with ERC20 interface and be able, for example, to deploy a Uniswap fork pool with meme tokens and so on. So this is our first case of composability and native interoperability with Solana. And also, the other really important part is the proxy. Our proxy, as you can see, it receives Ethereum-like transaction. It composes a Solana transaction and submits it to a Solana node. As I mentioned, we don't have a network of nodes. We started with I would say, only permissioned list of proxies that can run, but this is because of security reasons. On our roadmap, we have we're going to decentralize proxy operations, so anyone will be able to run their own proxy and to earn fees from submitting transaction to non-EVM and so on. So let's just go a little bit deeper and see how Solana programs, smart contracts, differ from EVM and basically the whole architecture. So the whole architecture of Solana is actually made in order to scale more. And the first and most important part is that programs in Solana are stateless. They don't have state. Smart contracts don't have state, but they save their state in data accounts. You can see program-derived accounts on the top. So you can imagine Solana being as a very big file system, and you have two types of accounts. You have executable accounts and you have data accounts. In data accounts, you have metadata that programs create those accounts in order to be able to persist data and read it. And in executable accounts, you only have the bytecode. In the context of Neon EVM is the only executable program in our infrastructure living in Solana. Everything else is in the form of program-derived accounts and metadata. You can see on the top corner, we have Neon account. This is actually represent an externally owned account, your MetaMask account, and you have in the metadata, you have the address, the balance, and everything else. And it's the same with contracts. You can see we have a contract account. We store the metadata inside this account, and also its storage. We persist it in program in PDAs. There are a lot of specifics here. I'm not going to go into much detail, but if there are any builders, for example, the first 64 storage slots are stored in the PDA that contains the bytecode, and the next ones are just if for example, you need to persist something on slot 65 or 66, you need to create a new PDA. Actually, not you, but Neon EVM will create a new PDA for you. And basically it will persist the data for this storage slot. So everything is abstracted away from the user, and from Solana perspective, these are just accounts that hold metadata. Let's now see how a Solana transaction differs from an Ethereum transaction. And we have a couple of important things, and one of the most important things that I want to talk about is the account list. So account list is actually a list of addresses of accounts that this transaction is going to access. Why do we need this, and why Solana team decided to put account list into the transaction is because of parallel execution. So this account list shows a list of accounts that the transaction is going to read or write from. And the most important thing is that if you don't have an overlap in two transactions, basically because of this account list, the Solana node can very easily filter out and order transaction that should be ordered simultaneously, and transaction that can be should be executed one by one sequentially. And our proxy, as I mentioned, is very important because the proxy receives EVM transaction, performs a simulation on a local environment, and finds out which accounts this transaction is going to read or write from, then puts this into the account list, composes the Solana transaction, and submits it to a Solana node. As you can see, the program index is also the Neon EVM program. This is the only program in our ecosystem. And also, we have some metadata, which is just related to the EVM transaction. We have nonce, we have gas price, value, data, and so on. And basically, this data is read from the Neon EVM program. It knows how to decode. It knows how to, for example, inside the data, we have the function signature, and so on and so on. So yeah, this is just a very simple diagram showing how basically the Solana node decides based on this account list which transactions can be executed simultaneously. As you can see, inside the node, we have a lot of transactions, not only for Neon EVM, we have all Solana transactions. And basically, transactions that are accessing different parts and different contracts will be executed simultaneously. That's why we have local gas fees and local gas markets. Something very important about incoming features, as I mentioned, we have our first use case of composability and interoperability is SPL tokens. But we have some more things to come. Bridges, we already have the bridge, which is actually supporting us, and you can transfer assets between, I think, 18 EVMs, maybe there are more, to Neon EVM, and also from Solana. But from Solana, you have the Neon Pass, our native bridge, which is actually very secure because you don't have, everything happens in one transaction. Neon Pass only computes the instructions for that has to be basically passed to the Neon EVM program. Multi-token gas payments. This is something cool. Users will be able to pay with their gas token of choice. For example, currently you are only being able to pay with Neon, but in the future you'll be able to pay with Solana, USDC, USDT, and maybe some more other tokens will be added. But and how this happens, we abstract away the whole logic on our side, and we'll have different RPCs. So let's say you will have a network that will basically, when you connect to it, it will show you your native balance in SOL, and you'll be able to pay with SOL. Same thing as for USDC, USDT, and all other tokens. And personally for me is the most important feature is general composability. As I mentioned, you can currently have natively ERC20 tokens that underlyingly are SPL tokens, but we want to achieve general interoperability. What does that mean? That means that from any from your EVM smart contract on Neon EVM to be able to call any Solana program. For example, you can build a DEX aggregator on Neon EVM that can basically route the users not only through Neon EVM DEXs, but also through Solana DEXs. For example, Orca, Radium. You can also, the use cases expand a lot, and currently this feature is deployed on DevNet. The integration team is actually testing the boundaries of this feature, creating some tools for developers. For example, we have built Solidity libraries on how to encode the code instructions, on how to, because in Solana, everything is base 58 and base 64 encoded, it's not hex encoded. And yeah, we're trying to build initially the tools, tutorials, before showing it to the wider audience. And yeah. Yeah, that was basically it. So I didn't want to overwhelm you with a lot of technical details because it took me around 3 or 4 months to understand what the heck Neon EVM is doing. And it's actually really, really complex thing. But yeah, if you have any questions, I'll be happy to hear them now or after my speech. If you find me anywhere, just say hi and we can discuss anything. Thank you.
Any questions? Just wait for the mic, please.
Real quick, so I just missed the start of the presentation, so I wanted to confirm, essentially what's going on is that the EVM bytecode is only being executed on the nodes themselves, never, for example, within the context of a Solana program, right? What Solana is being used like as a storage layer, essentially.
Not quite like that. So basically, even all the execution is executed on Solana. So yeah. On off-chain, we only do a simulation of the execution in order to determine the accounts we are going to access in this transaction and to compose the Solana transaction.
Yeah. Okay, great. Thank you very much.
Yeah. Maybe something to add. Oh, yeah. Okay. Yeah, something to add. About the composability, we have our own precompiles. And for example, we have a precompile that you can read data from any account. Actually, I showed this 2 days ago on my workshop in ETH Belgrade Hackathon, that you can read from your Solidity contract any data from Solana. This is how we read Chainlink price feeds and PIT price feeds from Solana. Yes?
What are the security risks of the Neon EVM approach, and how did you address them?
What are?
Security issues.
Security issues, basically, if we try to compare Neon EVM to any layer 2, I would say that we are way more secure because we don't have a separate network. We don't have a sequencer. As you can see, 2 days ago, I'm not going to mention one of the L2s, they stopped their sequencer because there was a hack. So currently, we cannot do that. Partially, because the security risks are in the proxy currently. And why is that? It's because, as I mentioned, we started with a centralized approach and whitelisted approach of proxies. Currently, we have P2P and Everstake to operate our proxies. We don't share it with the public. And this is because of how do we manage to execute iterative transaction? What does iterative transaction mean? Solana, in order to scale, is very limited in how many computational resources one transaction can use. In the EVM, it's 30 million gas. It doesn't matter how big your transaction. If it's up to the block gas limit, you would be able to execute it. For Solana, it's not like that. So sometimes, and a lot of times in DeFi, one Neon transaction actually equals to 20, 30, 50 Solana transactions. So we have divided it into two stages. The first is the EVM execution. So you execute all your smart contract code. You, on a separate data account in Solana, you write all the state mutations that you have to perform. And after that, you, in the last iteration, you perform those state mutations. And whenever this whole process goes on, we lock all those accounts in order to achieve atomicity. Because Solana nodes, you submit all the transactions in batch, and Solana node doesn't give you Solana doesn't give you a guarantee on how it will order the transaction. It doesn't give a guarantee. So we lock those accounts. And the only security risk is if we open source everyone to be able to run a proxy, there may be a malicious proxy that will lock some key accounts, for example, some assets, some contracts, and so on. So we are, with the new composability feature, we are pushing an upgrade that will be basically an optimistic locking, and we are going to remove this locking from the contracts. And optimistic locking means that in the beginning of each transaction, we are only going to save read and write revision of each account. And at the end of the execution, we're going to compare these read and write revisions. And if they match, if the data was not corrupted, we can finish the transaction. If not, we will retry it. So we will not lock any accounts after this upgrade. So the only, in towards the only security issue and security precautions are in the proxy. And currently, after this upgrade, there will be no real security issues. And also, we have 5 or 6 audits. I'm not sure. You can check on our website of our EVM.
Does that allow front-running the transactions, or no?
Front running from basically, yeah, you can front run transaction, but you can front run transaction in an EVM. This is not a security issue by itself. It's just a mechanic of how the network works. So you can, but we are also pushing EIP 1559, which implements gas priority fees. So users can decide what priority fee they want to put and if they want their transaction to be front-run or not. I mean, there's just a mechanic of how decentralized networks work. Yeah.
Thank you.
Thank you.
Do we have any other questions? All right. Thank you, Simeon.